Hey, so we've discussed the fact that we can have a pointer to a variable, and we can actually also have a pointer to a function. For this example, I have this function right here, void hello. So the return type is void. It doesn't have any formal parameters, and it's simply going to do console output hello human. And in the main function now, we can invoke that function hello by providing the identifier, in other words, the name of the function, in this case hello, followed by the parentheses, which is the function call operator, ending that off with the semicolon, and I'll build around that. From the main function, program execution will move to the hello function and we get the hello human printed out. Program execution moves back to the main function and we get end of program. Now let's do something silly here. What do you think is going to happen if you try and do something like this? We're trying to assign hello to x here. Notice that we don't have the function call operator here. Of course, if you do something like this, it's going to return void. So I have this example with the void hello purposefully here. If that was an integer and it is going to return an int, then we can assign that here to x. With variables, whether they are fundamental types such as x and y here, which is of type int, whether those are user-defined types such as classes and structs, we can assign them to each other, such as we can do y is equal to x. With this, we assign whatever x stores to y here, but we only use the identifier x and y. We don't have anything like that. So with the identifier with a function, you might be thinking, can we do something similar like that? We simply have the identifier of the function and we're trying to assign that to something to the left. I'll just remove those statements. Let's see what happens when we build this. Control B to build. We'll get a failed here. We cannot convert from this type, void, this weird type right here, to int. Okay, so this is basically the type that we have. So I'll copy that and I'll paste that in here. And if I remove this right here, we can see that we start to get something that looks kind of like a pointer. We have the void return type right here. And then we have the asterisk, and then we have the void right here. That's because the parameter list is empty. But let's go and look at another example. As a simple example, we have the square function now that is going to return int. The formal parameter is of type int, so it has a formal parameter now. Using the identifier, I'm going to try and assign whatever that returns to x. Try and build around that and we'll get an error again. Cannot convert from this type to int. So let's look at this type now. Again, if I remove this weird thing here, okay, we get int, which is the return type of the function. Then we get an asterisk again. Then we have another set of parentheses and we pass in an int. And this is basically the syntax for the type of a function pointer. The name is actually going to go in here. So I know the syntax looks a bit weird. I'll talk about this in a bit more detail here shortly. Before I summarize the syntax of the function pointer for you, I want to talk about this statement right here. So I do count square. Again, I do not have the function call operator here. I do not have the parentheses. It's not going to return something. I just have the name of the function and I can build around that. So as you can see, C++ will implicitly convert the name of that function to an address. We do not have to use the address of operator, but we can if we want. Okay, I have these two console output statements. In the first one, I do square here, and in the second console output statement, I have the square function name again with the address of operator. Build around that and we can see we get the same address for that. Okay, so with these observations out of the way, I'll just clean up here. Let's go and summarize the syntax for the function pointer. A program's instructions are stored in binary when we compile the program, and as with variables are loaded into memory when we run the program. This means as with variables, functions are somewhere in memory when we run the program and have an address. Now when a function gets invoked, program execution jumps to the address where the function starts. We have something called an instruction pointer, which is basically a register that stores the address of the next instruction to be executed. And so when a function is called, the instruction pointer is set to point to the first instruction of the function. This again is just a high-level example. If you want more detail on this, maybe take a course on assembly programming. But in this example, in the main function, we invoke that square function. In the console output statement, the instruction pointer will be set to the first instruction of that square function, and program execution will jump to that. Then program execution will move to the next instruction and so forth until we have all of those instructions executed within the function. You can think of these as the statements within the function. Following the execution of all of the instructions within the square function, program execution will return to the caller, which in this case is the main function. But the point with this high-level example is that functions also have an address in memory, And a function pointer is a way for us as programmers to assign that address to a variable. So let's go and look at the syntax for that. Okay, let's look at the syntax for declaring and initializing a function pointer variable. We do the return type and then parentheses. And between the first pair of parentheses, we do the asterisk followed by the pointer name. In other words, the pointer variable name. Then we do another pair of parentheses where we specify the types. We do a parameter list, which is basically going to match the signature of the function that we want to store in the function pointer. Now, as with the function declaration, we only have to specify the type, so a comma-separated type list. We do not have to provide parameter names, those are in the function definition. That is where we need that actual name or handle to use it within the definition. And of course, the comma-separated parameter list is going to be empty in this case, if the function does not accept any arguments. Okay, so that to the left of the assignment operator is going to give us the declaration for the function pointer variable. Then of course we want to assign something to it. So use the assignment operator for that, followed by the function identifier or name. It's important to omit the parentheses following the function identifier. You do not want to provide parentheses because we are not doing a function invocation. We simply want the name, which is going to return the address of that function, and we want to store that address in the function pointer. Again, it's similar to a variable assignment. We are only concerned with the identifier here. It's important to note that the return type and the parameter list of the function pointer must match that of the function whose address we want to store in the function pointer. I have a simple example of a square function here, which is going to return integer. The formal parameter is int p, and it's going to return p times p. The declaration for the function pointer variable in this example is int for the return type. In the first pair of parentheses, we do the asterisk followed by the pointer name. In this case, I'll just call it fptr for function pointer. And in the second pair of parentheses, we do the parameter type, so we do int. You can do int p if you want, but again, we do not need the parameter names. We can simply do a list of types that the function will accept. Again, the square function in this example accepts a type of int. And for the assignment, we assign the square function name to that function pointer variable. Again, notice in the assignment, we only do the function name. We only do square, so we do not postfix the square function identifier with parentheses. I know the syntax for the function pointer variable can be a bit weird, so I'm doing a bit of a comparison on this slide. In the first example, we have a variable pointer that we are familiar with at this point. These are referred to as raw pointers. In a future lesson, we'll learn about smart pointers, but we'll stick with raw pointers for now. In the first statement, we have some variable int x, which we initialize to 55. Then in the second statement, we have some pointer ptr, which is a pointer to an int. And we initialize that by using the address of operator, so we get the address of x by using the address of operator. And we assign the address that that operation will return to the pointer ptr. Next, we have the function and the function pointer from the previous example. Notice we can also prefix the function name with the address of operator, but we don't have to since the function is implicitly converted to a function pointer if needed. The goal of this slide is to show the similarities between a pointer to a variable and a pointer to a function. Hopefully this comparison will make the syntax easier to remember. In this example, fptr is a pointer to a function that returns an integer and has an integer formal parameter. Now of course the fptr function pointer can point to any function that matches this type. That again is a function that returns an integer and that also has an integer formal parameter. But in this example, we assign the square function to the function pointer. If you think about it for a second, you'll realize why we have to place the name of the function pointer between parentheses, right? So we have the parentheses, the asterisk, and then the function pointer name, in this case fptr. If you think about it for a second, what's going to happen if you remove the parentheses? So if you only have int, the asterisk, and then fptr. Well, in the case where we don't have the parentheses surrounding the asterisk and the function pointer name, that would be a forward declaration for a function fptr that returns a pointer to an int, and that has an int parameter. But of course we don't have a definition for such a function and we don't want one. We want a pointer to a function. So because of operator precedence, we have to place the asterisk and the function pointer name between parentheses. So there are some similarities between a pointer to a variable and a pointer to a function. We just have to get used to the fact that the function pointer name will be between parentheses, and that we also have to provide the parameter list. Now with pointers to variables, we can use the indirection operator. In other words, we can dereference the pointer to access a value indirectly. Now what can we do with a function pointer? Well, we can perform an indirect function invocation through a function pointer. In this example, I have the square function again, and in the main function, I have a function pointer declaration and initialization, so I assign the square function to the function pointer fptr. And as I mentioned previously, there's no need for the address of operator here. Next, we have an example of an indirect function invocation through a function pointer fptr. That is in the final statement in main in a console output statement. We do say out the stream insertion operator fptr, which again is the function pointer name. We pass in 5 for the argument, and then of course we do inline. And as you can see, there's no need for the indirection operator, that asterisk operator. We use the function pointer name as is, so fptr, the parentheses, and we pass in the arguments. With these examples out of the way, you can start to think how function pointers can be useful. You can use the type for the function pointer as a formal parameter in a function definition. but we'll discuss that later in the lecture. Okay, from the previous example we have this here. The fptr is a pointer to a function which is going to return an integer and takes in an int as an argument, or that has an int as a formal parameter. And as we can see in the statement, we can initialize that using the null pointer, so we assign null pointer to that. Then we can also do a check. I'll just go and make that p uppercase. That is for readability. We can do a check like this. I'll pass in the function pointer name, in this case fptr, into this check right here. So if that is not null, then we'll get not a null pointer, otherwise we print out null pointer. Build run that and we should get null pointer now. That's what we get. Now let's go and assign the square function to that. As I mentioned, you can use the address of operator, but we don't have to do that with the function. It's going to implicitly convert that to an address. Let's just build run that and we should get not a null pointer. Okay, that's fine, but how do we now use that function pointer? Well, in this statement right here, instead of printing out not a null pointer, we can call the square function via this pointer fptr. So what I'm doing is I'm dereferencing the fptr and then I'm passing in 5 for the argument. Just to show you, I can actually remove that address of operator right here as well. And I'll just put a space and build around that. And we should get 25 printed out. I mentioned the fact that we don't have to use the address of operator over here. Okay, we can simply specify the name of the function that we want to assign to the function pointer. Now similarly in this statement, we do not have to use the asterisk to dereference a function pointer. So I can remove the dereference operator. And so we can invoke the square function in this way without having to do any dereferencing. Okay, so I'll build around that. And you can see that works fine. To save some space, I'll remove that statement and I'll also remove the hello function. Now what happens if you don't have the function pointer name and this asterisk between parentheses? Well, if I go and remove those, I'll actually just build this so we can see we'll get an error here. We'll get this link error, link error, 1 unresolved externals. Basically, this is now a function forward declaration. It is no longer a function pointer declaration, and that is because the parentheses, the function call operator, takes precedence over the asterisk. Undo a couple of times. I'll define 2 more functions with the same prototype, so the same signature and return type, add and multiply. You can see both return int and have 2 ints as formal parameters. Add, of course, is going to return x and y, the addition of that, and then the multiply is going to return the multiplication of x and y, which is again the formal parameters. Okay, so back in main, let's say I want to change the assignment for this function pointer now. Okay, I want to assign add to the function pointer. Of course, we'll get an error here because the types do not match. Now these types should start to make sense. A value of type int, asterisk between parentheses, another pair of parentheses with the types int and int again, cannot be used to initialize that entity of type int, asterisk between parentheses, int between parentheses, where we need 2 ints between the second pair of parentheses, right? Now the prototype, or in other words the signature and return type of the function pointer, will match that of these functions. And in this case, we specifically want the prototype to match this of the add function, because we want to assign that, in this case initialize that to the function pointer. Then we do the check here, and then in the next statement we want to call this fptr. So I have to specify 2, that is provide 2 arguments. So I provide 5 and 5 for the arguments, and this is going to indirectly call the add function. Build around that, and we'll get 10 returned. Print it out. Now of course you can go and do printouts in this function, so add function invoked, you can do console output statement. In the multiply function, maybe multiply function invoked or something like that. But again, I'm just trying to keep this concise here. So what we have now is this function pointer fptr, which is a pointer to a function that returns int, and that has 2 formal parameters. In other words, it accepts 2 arguments of type int. And what's handy about this is this function pointer can now point to any function that matches this type. We have these 2 functions now, multiply and add. Again, they have basically the same prototype or a signature and return type. So we can initialize this function pointer fptr to multiply or add. So I'll change that to multiply, and now this fptr indirect function invocation should do 5 times 5, because that is defined right here in the multiply function. Build around that. We should get 25, and that's what we get. Okay, so that's another useful and important thing that I want to emphasize here. As with the raw pointers to variables, we can of course set that pointer variable to point to something else, or in other words store the address of something else. We can assign it to something else later on. So here I initialize the function pointer fptr to multiply, but here I go and assign add to fptr. In the next statement, we should get 10 printed out now, and that's what we get. Okay, so it's now going to indirectly invoke the add function. As with raw pointers to variables, we can use the const modifier. So we have the fptr. Let's say we want that fptr function pointer to be a constant pointer. So in other words, we cannot go and do this assignment now. We can initialize fptr to multiply, but we cannot go and assign to it later on. That expression must be a modifiable L value. Okay, so the compiler will enforce this now. If you try and build this, you'll get an error. You cannot assign to a variable that is const. Okay, so in this way we can have a constant function pointer to some function. Undo that. As a final demonstration, before I end this lecture off, I want to talk about auto, so automatic type deduction. Let's say we do this here, we have auto instead of this long type. As you have more and more formal parameters, and maybe some user-defined return type, of course, the syntax can get a bit complex for this. So we can do auto here. And then you can use the address of operator or not, it depends on what you want to do. Again, it is not necessary to use the address of operator. And if I do Control-K, Control-I here, we can see the type has been deduced correctly. What you do not want to do is you do not want to try and initialize that to null pointer. It will not deduce a function pointer type. The sort of syntax will work, it will deduce the type of fptr correctly. You can also use brace initialization, of course. Okay, so I'll do something like that. And I'll build a run just to show you this. It will build a run fine, we get 25 printed out. I'll undo a couple of times, and I prefer the syntax where we have the full type of the function pointer, but of course you can also use the brace initialization in this way. Build and run that, and that'll work fine. You can see. But the syntax can get a bit confusing because we have all of these braces now, and then we have the brace initialization as well. And with this, I prefer the C-style initialization with the assignment operator. Now, function pointers are really useful as function formal parameters, as we'll see in the next lecture. I'll stop this lecture here because it's getting a bit long, and we'll continue in the next lecture.